I'm Dina Smith. I'm the Associate Director here at the Observatory, and we're happy to have you all here for our Wednesday night lecture series. Tonight we have a talk by Stephen Swift from Woods Hole, and he went to Dartmouth in the 70s, did his undergraduate, and Oregon State in the late 70s, and then on to MIT joint program with Hui to do his PhD. And he's at Woods Hole now in the Geology and Geophysics group, and tonight we're hearing a talk called Drilling Fast-Spreading Ocean Crust in the Eastern Pacific. So, enjoy.
Thank you.
My connection with Western Observatory is through their Boston College Educational Seismometer program. That's how I got started. I do a little bit of geophysics down at Woods Hole, and that's what I'm going to talk about tonight. I was out for 2 months on the JOIDES Resolution, the blue ship, in the Eastern Pacific, drilling ocean crusts, and I'm going to actually give 2 talks tonight. The first one will be about why we went and what we were going after, and some of the geophysical results that I got from the cruise. And then the second part will be pictures from the cruise, pictures of the ship, how the ship runs, things that happened on the ship. So let's get started. Let's start with why we. Let's start with vocabulary. We'll do vocabulary first. I'm going to talk about rocks. I'm going to talk about rocks from the ocean, and mostly about 4 types of rocks. And I brought samples here, and you're welcome to look at them now and pass the samples around if you can. Well, one of them's very heavy, or you can look at them afterwards. The vocabulary words are basalt. Basalt is the rocks we find on Iceland and in Hawaii. They're what forms the upper part of the crust. This is a piece of rock from a pillow basalt. It's got nice shiny glass on the top of it and lots of pores on the inside. And one of the characteristics of this is it's got high porosity. I'll be talking porosity, and that's just the amount of air or seawater that's inside the rock. So
Where's that from, Steve? Is that Hawaii?
No, it's from the seafloor. I'm guessing the Eastern Pacific. The second rock that I'm going to talk about are diabase dikes. They're actually the same chemical composition as basalt, another black rock. Porosity is much lower though. And a dike rock is an intrusive rock. So that's sort of an extrusive rock. It's something that erupted on the seafloor. These are rocks that get injected inside the crust, and I'll show you some pictures of what the structure is actually like. But if you get up close to this and look at it, there's actually 5 different dikes that are in this. So there are 5 different episodes of magma that got injected up, and then the rock solidified. The crystal size is much smaller, and the porosity is much less. I'm not going to pass this around because it's kind of heavy, but you can look at it afterwards. The third rock type is a very important one. It's called gabbro. It's got a different mineral and chemical composition, but it's than basalt, but it's very closely related to it. The main thing that you'll notice is that the crystal size are much, much bigger. So you can even see from there, you can see the crystals. And this is generally thought to be the kind of rock that solidifies very slowly. It's sort of like the granites that we have, but it's got less quartz in it than the granites that you find in New Hampshire and in Massachusetts. I'll pass that one around. And the last rock sample that I brought with me is a sample from the mantle of the Earth. This is below the crust. So this nice green rock in here is a harspergite. You don't need to know the name. But the key thing is it's made mostly from olivine, which is a very green mineral. So you get this nice green. This is the rock that is in the upper mantle. In this one particular sample came from the continent, so it's a continental mantle. It's all pretty much the same. So dikes, porosity, basalt, gabbros, and mantle. We're all going to talk about that today. All right, this is the part of the talk where I tell you why we did this. This is why it's important. I'm going to be talking about ocean crust, which covers about 3/4 of the Earth. So what the ultimate goal of all this work was to try to understand how this crust formed. And for reasons I'll explain a little bit later, it's not that easy to find out. We look at it with geophysical tools, with sound, and we can drill it. But they've been trying to drill since the 50s with the Moho project off of Mexico, and that didn't go so well, and we're still having our problems, as I'll describe. So even though we've been working at it for a long period of time, there's still lots of things that we don't understand about it. What's important is that it covers most of the Earth. The other important thing about it is that much of what we sense as animals living on the surface of the Earth came from inside the Earth. So when the Earth first formed and solidified, there was, since that in the last 4 billion years, there's been a lot of volcanism. And a lot of this volcanism is oceanic type volcanism, and this is where our atmosphere, this is where our water came from and where it's still coming from. So we want to understand something about that kind of a process, and that's why we're studying ocean crust. More recently, a reason is that people have begun to find bacteria and animals living in the basalt. So not only are there critters crawling around on the seafloor, worms and things like that you might have seen in pictures from black smokers at Ridgecrest, but we get down inside maybe as much as 100 meters or more, and they've been finding bacteria. And this is something very new, and they're trying to understand something about how important this is in the history of evolution. It's one of the key things. So and the astrophysicists are actually, we have an astrophysicist in the back, are actually interested in it because they're looking for analogs with Mars and places like that. This is a picture of the age of the Earth, age of the ocean crust. The red is the youngest. The blue out here is something like 160 million years old. So all our ocean crust forms by seafloor spreading at the mid-ocean ridges. It spreads apart. We're not quite sure what drives it. There are lots of theories about what drives it. This is where the youngest crust is. I'm going to be talking about fast-spreading crust. And fast-spreading crust actually doesn't make up a long part of the present mid-ocean ridge. I'll show you a picture. This is probably the area where the fastest spreading crust is in the ocean. But if you actually add up the amount of ocean crust that was formed by fast spreading, it's by far the majority. So over 50% of the ocean crust was formed out of fast spreading crust, even though it's only a small portion of the mid-ocean ridge. If you took a cross-section through the North Atlantic looks like from Florida over to Africa, it looks something like this. At the mid-ocean ridge, the ocean plates are spreading apart. There's hot magma. There's mantle rock that's rising, and as it rises, it melts, and that melt, by some process that we don't understand very well, gets channeled up to a very narrow spot in the ocean and erupts and forms ocean crust. The ocean crust is this little black line. This is all mantle down here. And continental crust is this gray part over here. But the part I'm going to be talking about is just this thin layer on the surface. This is a general idea of looking shallower. We're down here from 0 to 10 kilometers. And this is a general idea of what the structure is of ocean crust. At the top, we have basalts, eruptive basalts, These vertical lines are the sheeted dikes, that big rock that you haven't seen yet. Then the gabbro is below that, and then the mantle, the green rock, the peridotite, is where the melt starts. So the general idea is the melt comes up, somehow it collects in something that we call a magma chamber, but it's kind of, we don't really understand it very well. And from that, basalt erupts, makes sheeted dikes, and erupts on the seafloor to form the basalts.
Steve, is the peridotite, does that correspond to the olivine-rich
Yes.
sample you showed?
Yes, exactly. Looking down even smaller, if we look at this area right up here, right at the ridge crests, important thing happens. As this hot magma is coming up and being ejected, all these rocks are very hot. And that heats up the seafloor. The rocks are also cracked because they're spreading apart. And they spread apart as magma injects up into them and erupts on top of them. But they're also being pulled apart and stretched, like you'd stretch a dinner roll. And as you stretch it, it forms breaks and cracks. And that allows seawater to come in and begin to circulate. It gets in, gets near the hot rock, heats up, comes out in black smokers. And this cycling of rocks, of seawater, is very important because it brings minerals from the seawater into the crust, and it also leaches some minerals out and deposits them at the seafloor, or they get injected up into plumes and drift away. And then there are actually places in the eastern Pacific off Peru where they were called metalliferous sediments, where there's so much metal being deposited from these plumes that the seafloor sediment is very rich in iron and manganese and things like this. So this is a very important process, and one of the things that we wanted to study. We can't study this process directly because the rocks are so hot. They're also very crumbly, and we've tried to drill here over the last 40 years and not done a very good job. We've only got about 10 meters deep. So we can't drill very well. So one of the things that they did very early on, and I think this is a picture from the 40s or the early 50s, is to use geophysics. And back then, they would throw dynamite over the side. This was probably a 5-pound charge that they would throw over. They would listen to sounds with sonobuoys, which are a military instrument that they developed during World War II. They're essentially a hydrophone on a buoy with a radio transmitter. And the military used them to listen for submarines. But what they would do was what the geophysicists would do would drop the sonobuoy over the side, steam away, drop charges, and listen to the sound. And unfortunately, I came along too late to throw dynamite over the side of a ship. So this is what they were doing when I came along, and this is a picture of something that I used on board the ship to do my geophysical experiment. And it's something that all the geophysical experiments that are done in the ocean now use, and industry uses it as well. It's called an air gun. Essentially, it uses compressed air that comes in through one of these hoses. It builds up a pressure in one of the chambers, and then it's triggered and it vents. It produces a bubble of air down at 10 meters or so. The air rushes out, it overexpands, gets very big, and then all this pressure suddenly begins to act on it, and it collapses in a big bang. And that produces a nice impulsive sound source. When we want to look at really deep, they put 20 of these things over the side. And when industry goes out, they'll probably use 30 of them at a time. But we just use this one for my experiment. Wasn't very big, that's a credit card right there. But using these kinds of things, we collect data like this. And this is a record of seismograms that were collected from a hydrophone that was down at the seafloor right at this drill site. And the range over here, they're plotted against range from 13 to 0 to 12. So it's about 25 kilometers distance Time goes this way. So they plotted, and as the signal arrives, then you start hearing other things coming in from behind. And I'm not going to go through this. This is just to sort of show you what the data was. Someone picked these colored lines, and then using a lot of modeling and mathematics, what they come up with is a profile of the velocity at that particular spot. And they get something that looks like this, which is velocity versus depth in the seafloor. And these are some old results that were done with dynamite on the East Pacific Rise. And then these are some sets of results that were done in various different ways at another drill site that got very deep closer to Panama, called hole 504B. And I'll show you, we'll talk about this a little bit later. This is the deepest hole. This got down to 1,800 meters into basement, which is about a mile into basement. And what people have found by doing these kinds of experiments in the Pacific and in the Atlantic and in the ocean is that in general, the velocity increases from 3 or 4 kilometers per second down to about 2 kilometers depth, and then there's a very homogeneous layer. So there's a lot of variability up here, then there's a homogeneous layer, and there's a jump when you get down into the mantle rocks. That's what you found at 504B, this steep increase, this change, this layer, and then a jump up to 8 kilometers per second when you get into mantle. And this is what I was doing my experiment about, because we don't really understand what this change is right here. What changes when you go from this sloping region to the homogeneous region. There's only one place that we drilled it, and that was at hole 504B, and this was in the sheeted dikes, in the dike rocks. And I wanted to do this again at someplace else to see if that was really the case. So that was what my experiment was. My project was to collect some velocity data in the upper part of the hole. Okay, there's another way that we can understand what is in ocean crust. And that is because there's lots of strange tectonic things that happen in ocean crust and in continental crust. And one of the strange things that happens rarely, but often enough, is that a piece of ocean crust will get pushed up onto land. And we can tell that comes from the ocean crust because we can look at the sediments that are on top of it, and we can see that they're all filled with marine fossils. All the kinds of things that we associate with ocean sedimentation we find in there. And we find a certain stratigraphy in these rocks. And one of the best places for this is a sequence of rocks that happens in Oman, up here off of the Arabian Sea. There's a really long stretch of what appears to be ocean crust that got shoved up onto land. Well, you say, why can't you just learn everything you want to learn from these things? Well, it's never really been clear. There are lots of indications chemically that the ocean crust that formed these things was different than what formed most of the ocean floor. And the other thing is, they got shoved up on land. And when they got shoved up on land, they got busted up, and lots of things happened to them. And so they aren't a perfect representation of ocean crust. We can learn a lot from them, but and people still study them. Here's the same sequence we have of sheeted dikes and extrusives, gabbros, and going down into mantles. So the whole sequence is there. But you can walk around and take pictures of it and take samples. So this is what the uppermost igneous crust looks like. These are pillow lavas, pillow basalts that where you get an eruption, squirts up, forms a nice round ball. And underneath that, you get lava flows that are more massive. You get deeper, and you see sheeted dikes, and you can see these vertical dikes They're all intruded. What you have, what we think happens, and what we can tell sort of from looking at earthquakes on mid-ocean ridges, is that actually you get swarms of earthquakes. And we think that this happens when a dike gets intruded. It starts at one end and it goes shooting across. Not shooting across. It's not. It's maybe 2 or 3 miles per hour. We'll see a sequence of earthquakes, and we think that that's when one of these dikes gets intruded into the ocean crust. Underneath, we get different kinds of gabbro. You can see the coarser crystals that we get down there. And this is a general sequence in cross-section with the sediments, pillow basalts, sheeted dikes, and a thick sequence of gabbros, and then things that we associate with mantle, lots of different kinds of rocks. So the big question that I wanted to answer on this cruise was, how do we associate this kind of sequence of rocks with the geophysical sequence, the velocity profile that I showed you? So what have we done in 40 years of drilling? This is a plot of age of the ocean crust versus depth below basement, and it's a record of all the holes that we've been able to drill in ocean crust. And this one long one over here is 504B. That one got down to 1,800 meters. And this is the one that we drilled. It was actually 3 legs. The leg that I went on was the third. And I was talking to somebody today, and he said, oh yes, we're all excited. We're going back and drill it deeper. So this is one that we'll keep drilling. All these went through the lavas and into the sheeted dikes with about 100 meters to 150 meter transition zone between the two of them. But up until our cruise, nobody had ever gotten down into the gabbro. We had never seen this transition between the basalt and the gabbro. And some people thought that transition in the velocity might be associated with that change in the rock type. This is the same information, but it's plotted against the rate at which the ocean crust spreads. From very slow, like in the Atlantic or up in the Arctic, in the Southwest Indian Ocean, intermediates that we might get off the west coast of the United States, to very fast crusts. This is, someone told me, ocean crust spreads at about the rate that your fingernail grows. And the crust that we were on, which is about 3 centimeters per year, this was almost 100 times faster, maybe 80 times faster. So it's that big a range of rates of ocean crust spreading. The units are a little different than what I just told you here. These are millimeters per year, 1/2 of the crust. So this is a map of the ocean spreading centers in the ocean and the rate at which crust spreads. You can see the fastest rates. You get up to 150 millimeters per year, and it's down to 18 up in the North Atlantic, and down here we're at 2, 14, 2. So there's quite a range of spreading rate. Okay, so there was a scientist, geophysicist at University of California, Santa Barbara named Doug Wilson, who wanted to find out what the ocean crust was made out of. And what his bright idea, he was the one that started the hole that I was drilling on. His bright idea was, if you look at the geophysical data from spreading centers, where you get down at some point, there's a very noticeable change in the velocities. It actually inverts. So instead of increasing with depths, it actually gets slower with depth. And they associate this with a place where the rocks are very hot and maybe partially molten. If you do those geophysical experiments right on the ridge, for many different ridges of many different speeds, you can plot the depth to this inversion, or possibly to the magma chamber, versus the spreading rate. And what you see is the thickness gets less as you get faster. And this might be sort of intuitive. If you're pulling apart the plates faster, you get more hotter rock gets up to shallower depths. And this was 504B, which never got down to the depths where you might expect the gabbros or the magma chamber. And Doug's bright idea was to go out here to very fast spreading crust, drill a hole so you could get to it without having to drill so deep, without having to do so much work. And he was right. He picked a spot here in the Eastern Pacific. This is the site that we drilled here. It started with leg 206 and I think leg 206 was in 2002. And in 2005, in the summer, they went back for leg 309. And then the leg that I was on was in November and December of 2005. Very fast spreading crust. It's nice because it's right on the shipping route from the United States into Panama Canal. So there was lots of chances that you could get the ship to that point. Instead of being off in the Northwest Pacific, there was a much better chance that the ship would pass by this area and we could do multiple legs. So Doug went out and did a survey. This is a bathymetry map. This is 10 kilometers down here, which is big, but in this map, there's only variation between 3,300 meters to 3,800 meters. So there's only 500 meters of seafloor variation over this wide area. So it's very, very flat. And it's very unusual in that sense, but very attractive to drilling. And they picked a spot here because it was flat, because it wasn't near any of these other bumps and ridges and seamounts. And they did that geophysical experiment that I showed you. And these are two results from the hole. And they show the same profile where the velocity increases with depth fairly rapidly. It reaches some nick point, changes. It's very homogeneous down until you get down to the mantle rock. So what is this thing right here? Well, we thought that we could drill to that spot on this leg, but we got just above it. And this is the history of drilling in the hole. This is days in the hole for each of the 3 legs that we went out. So this is leg 206, 40 days. Leg 309 went out for about 40 days, and we were out there again for something like 40 days. They got very good penetration at the very beginning. They got deep quickly, covered a lot of ground. That went well. It got a little bit slower when they went out the second time, and when we got out, it was terribly slow. But this was sort of what they'd found on 504B. When you get down into these sheeted dikes, for some reason, the drilling slows down. But this is one of the main things that we achieved is they actually did, at the end of our leg, we drilled through the sheeted dikes and into gabbro rock. And I'll show you a picture of that. So we actually, and that particular depth that we drilled through was within 10 or 20 meters of what Doug Wilson had predicted it to be. So it was a remarkable piece of geophysical prediction. So these are some of the rocks that we got. They're like those rocks that I'll show you, that I have shown you. Some basalts, pillow basalts, a little bit of breccias, only a few percent of breccias. Mostly these sheet and massive flows, 90 to 95% of them. And then dikes. This was the record from leg 206. They hadn't gotten down, they had just barely got into the dikes. Leg 309 got almost all dikes, and on our leg was mostly all dikes as well. This is a dike rock. And I mentioned to one of the petrologists, gee, that looks like a very dull rock. You know, I grew up in New Hampshire, and I've looked at granites and seen lots of quartz and mica and lots of interesting minerals in there. And this looks really uninteresting. And she said, oh, no, this is very pretty rock. This is a very pretty rock. You just aren't looking at it right. And so what they do on board the ship for the petrologists to be able to identify the minerals is that they take a slab of the rock and then they sand it and thin it down to so it's so thin that you can put light through it. And once you can put light through it, then you can begin to identify minerals. And this is what it looks like. So this is maybe a millimeter across some of these grains. And she said, this is what you should be looking at. And I don't know, I can't pretend to accurately identify all these minerals. This looks like plagioclase, but it was clear that once you look at these things on a microscopic level, that they're a different kind of thing. It's not all very plain. You see lots of veins, places where that seawater has gotten down and altered the minerals, altered the rock. You can see it's a little bit greener right here along where the seawater passed through a crack. There's lots of this alteration in these rocks, and some of the rocks are almost totally alterated. This is the actual contact between dike rock and gabbro. The cruise was an international one. The two countries that do most of the put up most of the support for the drilling at the present time are Japan and the United States, and it's about 50-50. But there are other countries that put in lesser money, and those include Europe, and we had a lot of scientists from England, a few from France, from Italy. We also had them from Chile and Korea. So it's a very international thing, and the British at one point decided to lay claim to the gabbro dike contact. These are some of the gabbros. If you didn't see the rock, this is a gabbros, much more coarsely crystalline, lots of big crystal grains. Some of the gabbro was darker with more manganese-rich minerals in them. A lot of variety in the gabbros. When the mineral really alters with seawater, it can alter to greenish colors and red colors. It depends upon what minerals get leached, what elements get leached in and what elements get leached out. Okay, when they're all drilling, all the geologists on board want us to drill right to the very end, to the last minute before we head for port. But when you drill, you don't always get samples. You try to get samples for 100%, but you don't often do it. And in fact, there were some cores that we took that we didn't get anything. So we know that there's a lot of the borehole that we don't have rock samples from. And so what you can do after you finish getting the rocks back is you can put down instruments that will go down in the borehole. They're on a wire line. They go down into the crust. You bring them back up through the crust, and you can measure the geophysical properties, the electrical properties. You can measure the porosity, all sorts of things. We call this logging, and it's done at the very end of the cruise. And one of the tools that they put down is a seismometer. If you go on the way back out, if you go into the other building, you can see the seismometers that are here at Weston. But people have condensed those things down so that there's actually 6 of them in one of these borehole tools. It goes down, and that's my seismic sensor. We put this air gun over the side, and we hang it from a buoy. It was down about 20 feet below the sea surface, suspended on a buoy. And you can see the air bubble coming out after we've just shot it off. So we have a sound source at the surface. We have our seismometer that's clamped down in the borehole. We shoot to it a couple of times, and then we stop the air gun and we move the seismometer. So we've got a sequence of shots that we collect as we go up through the borehole. There were actually 2 of these experiments done. One was done on the first leg. That's these are the data from that experiment. And what you see is this is from borehole depths of 300 meters down to 750 meters. And as you get deeper in the hole, it takes longer for the sound to go down. This is time, from 2.6 seconds to 2.85 seconds. So as you get deeper, it takes longer for the sound to get down. Well, you can, just looking at this, you can say, well, here's a way I can figure out how fast the rock is. I can just pick these times and figure out what the velocity is. And that's essentially what I did. This is the data that I collected on my cruise for 350 meters down to about 1,500 meters. The same thing. It takes about 2.5 seconds for the sound to get down there. And from this data, you can figure out velocity. This is the travel time. So if I pick the travel time to each of these seismograms, I could plot it up versus depth. And from the slope of that line, I can figure out velocity. So that data is this red line was the shallow experiment that was done in the first leg, and the orange line is the velocity profile from the leg that I was on. And the pink line is the line that they did, I showed you at the very beginning with the geophysical experiment with the hydrophone sitting up at the top of the sediments. So we're all very close together. There's a little bit difference up here. This has probably got something to do with the fact that this experiment was done over tens of kilometers, whereas this experiment was done over a few meters around the borehole. So there's a lot more. This result averaged over a much bigger area. So this was the logging velocity that they took with the tools that they ran down. And this is the electrical signal and the porosity that they got from those tools that they put down the hole. And what you can see is they all go in the same direction. The other thing that I'll show you pictures of is that we take samples from the cores that we get back up, and we cut little cubes, and we make all sorts of measurements on them. The igneous petrologists look at the thin sections of them. The chemists grind them up and do chemical analysis on them. And what I measured is lots of these physical properties. So these are bulk density and porosity of the samples from the very top down to the very bottom of our hole. This is the velocity that we measured, and we can also measure the thermal conductivity. And this is the last slide that I'm going to show you about the science. This is a plot of porosity versus velocity. And what I think that this shows, the last group that I gave this talk to disagreed with me on it. So you're quite welcome to question me on this. But what I thought that this showed was that as the porosity decreases, the velocity increases. And that these are results from logging, porosity measured with logging and velocity measured with logging. And these are the results that came from the laboratory experiments. And what I think is that the thing that controls the velocity in upper ocean crust is how much porosity, how much pore space there is in these rocks, and not the minerals. It's clear that the minerals change, but to me, the thing that explains maybe 90% of the variation in velocity is this porosity. So, are there any questions on the science part of this talk? Because I'm going to change.
So the conclusion was that at the bend, what did you conclude from the bend? Say that again.
What's the bend?
Where that transition period?
We don't know. We didn't drill through it.
So
We
you
got down
just-
right to it.
Okay.
But right at that spot, was also about the same spot where we got into gabbro. So the scientists who long ago thought that bend had to do with basalt up above and gabbro down below think that that's what what it is. But this other hole that we drilled in, we get to the bend and it's still in the dike, so it's not real clear.
Start with,
I'm going to show you.
what's that?
I'm going to show you. What you do is you stick a funnel down on the seafloor, and the funnel sticks in the seafloor, and then below the funnel you hang steel pipe to keep the sediment from flowing into the hole. And so I'm going to show you some pictures of that funnel that sticks in the hole, and then there's a funnel where you go down and you put it right in there, and I'll show you how we did that.
What's that, and then a big pump?
Well, we don't know. That's the whole point. That's why we keep going back after 40 years. We still haven't gotten down into it. So we keep going back.
The drawings in the book are fiction to some extent.
The drawings in the book come from the exposures on land. The drawings in the book, we still haven't proved that, it's still like it's a hypothesis that that's what we should find if we drilled into ocean crust.
But they have different seismic properties. that you-
The different kinds of rocks,
Right.
we can't distinguish them based on the seismic velocities. Yeah, they tried that and it doesn't work. It doesn't. What I think my results say is that the seismic properties are controlled by the porosity of the rock, and don't have anything to do with whether it's gabbro or basalt or porosity.
How much depth is on the part of the ocean that's kind of not on land? How deep, what's the equivalent depth of how far they can look at stuff on land?
On land, have they gotten deeper on land? They have. There are deep holes in Germany and in Russia, and they're trying to do. They haven't got many deep holes in North America. They're deeper than that. They're deeper than 2 kilometers. I'm thinking 4 kilometers or something like that. But they run into problems on land because there are faults and there are zones that are hard to drill through. And then the rocks get hot and you can't drill in the hot rock.
Reasonable.
Okay, so this is the fun part of the talk. This is how we did it, part 2. We started in Acapulco and we ended up in the Panama Canal. Beautiful Acapulco hills. We sailed on the blue ship, not the white ship. The blue ship is, the Joyde's Resolution is, it's 470 feet long. The ships that I usually sail on, the largest are about 300 feet. So it's a big boat, and it's nice to be on board because it doesn't rock very much. Though it has gotten banged around. There was a time in the North Atlantic that it got smashed and waves broke glass up here on the bridge. So it's been in some rough water, but when I've been on it, which is 3 times, it's generally been nice and flat, and no one gets sick, and it's very nice. Obviously, if you get into these bigger boats, it's even better. This is not the biggest. This is the boat that has done most of the scientific drilling in the oceans. The Japanese have just built the largest ocean drilling ship in the world. It's bigger than anything that the industry used. This is sort of a standard industry-sized drilling boat. In fact, we almost lost it to industry because the price of oil went up. The people that own the boat were offered more money to put it into drilling for oil. But we managed to get a lease with them to continue drilling for another 10 years. The Japanese build one that, let me see if I get this right, it's 690 feet, 470, so it's 690 feet. So it's almost 1.5 times longer than this boat. This is the Chikyu. This is it on its first test. It's a huge, huge thing. It's one of the biggest boats in the world. It's a gigantic thing. There are maybe a dozen stories in here in the stack of laboratory space. And it holds 10 kilometers of pipe on it. And they're still testing it, so it's going out for trials, but this will be the next, in the next phase of drilling, they'll be drilling from the Chikyu as well as from the Joyde's Resolution. The first thing that the Japanese want to do is to take it to one of these subduction zones where there are lots of earthquakes off of Japan, and to try to study the source of all these earthquakes off of Japan. That's what it was built for, as well as for supporting the Japanese shipbuilding industry. Okay, the ship is sort of divided up. The front end of the ship is where we lived and where the science labs were. As you got farther back, you got into the area where most of the drilling happened. There's actually a hole in the middle of the ship, a moon pool where the pipe goes down through. And then there are lots of, in the after part of the ship, there are woodworking shops, metal shops. And at the very back is a helicopter pad that we use for medical emergencies, and what industry would use if you were sitting on a hole for months and months at a time. They could transfer crews back and forth with helicopters. But the captain, when we got on board the ship, and the captain gave a talk about the ship, he mentioned that there were 1 mile equal 21 laps around the helo deck. And I found out from the doctor later in the cruise that the captain lost 40 pounds in the last 6 months by walking out back here. This is the helo pad from a webcam that's on the bridge at the Panama Canal. So you're actually looking down at the helo pad, and this is a picture from the helo pad looking up at the derrick and the draw works. This right here is a hydraulic system that they use to take the heave out of the ship, so that when the bit is down on the seafloor grinding away, drilling a hole, that it doesn't go up and down as the ship goes up and down. So this absorbs most of the ship's motion, so that the drilling motion is rotary and not banging like this. This was the first ship that I was on that we could make regular telephone calls. For as long as I've been going to sea, we could make telephone calls, but there was cost of $10 or $20 a minute by a satellite phone. But they had just got some new satellite connections in, and you could use voice over IP connections to make telephone calls for the price of a long-distance telephone call from Texas A&M, which operates the ship, from College Station, Texas, to wherever you wanted to call. So it's very cheap. We could get we couldn't get broadband, but we could get internet connection, so you could get information while you were out at sea. And the other new thing that I experienced on this trip for the first time, which the military has had for quite a while, is satellite TV. Navy ships have had this for quite a while, but this is the first ship on one of these antennas is a TV antenna, and one of the things we found out, so you could get Armed Forces Network TV out there, which was nice. This was November and December. That's football season. So football games were a big thing with the crew. But it turns out that the signals from the satellites don't go through the derrick. So if we happened to be on the hole and drilling, and the derrick was in the way, then the navigators had to move the ship so that there was a direct line between the dish and the satellite during the football game. It was very flat weather. This was the worst weather that we saw. This is a water spout. That's the sea surface down there, and you can see a little water spout. But in general, we had very nice weather. Nice sunsets, lots of clouds, but often nice sunsets. This is a picture from up in the derrick, looking down at the joints of pipe. Joints of pipe are about 90 feet long, and they weigh 2 tons. So these are the sections of pipe that they would string together to go down to the seafloor. Seafloor here was about 2.5 kilometers. We could get down in about 6 or 7 hours, I think, to get the pipe down to the seafloor. These are the racks of pipe. There's a very, very elaborate hydraulic system for for managing the pipes, for bringing pipes up and getting them up to where the drillers can get a hold of them and put them onto the drill floor. And there are all these catwalks, some of which are open, some of which are closed. You can get around on the ship. So being outdoors is actually kind of dangerous, and it's dirty because there's oil everywhere. The navigation. This is the chief navigator, and he is struggling with a transponder. And this is what we would, they would put a weight on this, put it over the side. I think there's flotation in here, so it would come back at some point. It would sink down to the seafloor. It's got a beacon on it, so acoustically you could navigate the ship from it. In fact, I think they need, in these water depths, they only needed one of these. So they put a hydrophone over the side of the bow of the ship and the stern of the ship, and there's enough distance between the two of them that they can navigate down to a single beacon on the seafloor. And using that and these computers, they could keep the moon pool, the place where we put the pipe through the ship, they could keep that within about 10 meters of the drill hole for 40 days. So we never drifted more than 10 meters, more than 30 feet away from the spot where it went into the hole. It's sort of an ad hoc system. They always have somebody on duty watching the things. It's supposed to be automatic, but of course when you have a football game, you have to modify things a little bit. But it worked very well.